So let's try to find some other groups of order 4. And by order 4, I just mean size 4. When we say the order of a group, it means its size. So we found a bunch of groups that were isomorphic to Z4. So let's try to find some groups that are isomorphic to something else of order 4. Or groups of order 4 that are isomorphic to something else. So maybe we could look in the UNs. We could try U10. That would give me 4 elements, right? Because what are the elements that are relatively prime to 10? Well, 1, 2 doesn't work because the GCD of 2 and 10 is 2. 3 works. 4 would not work because the GCD would again be 2. 5, the GCD would be 5. 6, no, it's even. 7 and 9. And if I do this, I find, by the way, I'm going to write it like this to make it obvious. I find they get the same group we had before, unfortunately. You see, 9 times 9 is 81, which mod 10 is pretty easy to see that's 1. Just look at the last digit, right? 1. And I have to have a 7 here and a 3 here. We're just playing some Sudoku at this point. Let's see, 7, 3. I need to have a 1 and a 9. Okay, so over here I do need to know what's what, but 7 times 7 is 49, so this is a 9, that means that's 1, that's 9, and that's 1, and I have my table. And unfortunately for us, it has that diagonal pattern, and it turns out that 9 and 1 are their own inverse, and that 3 and 7 are inverses of each other, so I did not get a new group. But there are 2 more groups of the form UN which have 4 elements, and those are going to be U8 and U12. So for U8, let's draw them side by side with U12 being over here. Okay, so what are the elements that have a GCD of 1 in the set from 1 to 7? Well, the odds, right? Because 8 is 2 cubed. So anything that has a factor of 2 is not going to have a GCD of 1. For U12, what are my elements? Well, no 3, no 4. I have a 5, but no 6 with 12. I have a 7, no 8, 9, no 10, but I have an 11. Okay, so I can do the identities here and here, because if we multiply, we obviously get everything back if we multiply by 1. Now, 3 times 3 mod 8 is 1, and 3 times 5 is 15, which mod 8 is 7, 1 away from 16, and 3 times 7 will give me 5. And also, it's commutative. I should just say A times B is B times A, which means commutative. So I could do that. And now I have a 3 and a 1. 5 times 5 is 24. No, it's not. It's 25. But what I wrote is 1. I wanted to say, is 1 more than 24, which is why there's a 1 there. My words came out different than my hand and brain there. 5, 4, 1, 3, 5, 7, 1, 3, 7, 5, 3, and 1, because 7 times 7 is 49, and 48 is divisible by 8. Now over here, though, with the 12, what do we get? We get 5 times 5, which is 25, which is 1 more than 24. And 5 times 7 is 35, which is 1 less than 36, so I get an 11 there. 36 is evenly divisible by 12. And 5 times 11 is 55, but I know that has to be 7 at this point. And now let's see, 7 times 7 is 49, but 12 goes into 48, so that's a 1. 1, 11 times 7 gives me the 5 and the 5. Now notice this. I still have this diagonal here, and I still have this diagonal here, just like I did with these groups that are isomorphic to Z4. But there's something a little different here. I have a diagonal here, and I have a diagonal here. Now you might say, okay, wait a second. I object, or I have a question. You might say, what if I reorder the elements in these cases? So what if I reorder these numbers, I put them in a different order? Would that other diagonal go away? And the answer is no. The other diagonal would not go away because in this situation, every element is its own inverse. The inverse of 1 is 1, 5 is 5, 7 is 7, and 11 is 11. No matter how I reorder these numbers, I'm going to get that. I'm going to get 1, 5, 7, and 11. Each one is their own inverse, so each one is going to have the identity down this main diagonal. And I get the same thing here. No matter what I do here, I'm not going to get that. Because the only ways I could get all 1, the only way in which I could get all 1 down that main diagonal is if every element was its own inverse. Because that would imply whatever here times whatever is here times itself would give me that identity. So what we have done here is we have found fundamentally different groups. So yes, the group of complex numbers is the same as Z4, which is the same as that special group I made with the EABC, which is the same as U10, and the other one that we were just talking about before, U5, all the same. But these two are different. So there's not just one group of order 4. No relabeling is going to turn this into this. And that's important. Is there anything else that gives us this as our option? Is there anything else that gives us that? Well, let's try to look at what other groups of order 4 we can construct. But maybe let's do that in the next video.